All right, so we are going to talk about two different types of cells. Now, these are two fundamental cells. We have galvanic, also known as voltaic cells. And then we have electrolytic cells. All right, and then we're going to kind of go over the differences and how they look and stuff like that. So these, as you might have guessed, are going to be spontaneous. So this is kind of the main difference, and these are non-spontaneous. So when we talk about electrolysis or electrolytic cells, non-spontaneous cells, you need an extra energy source to be able to charge them up. So think about when you're charging rechargeable batteries. The battery's dead, but now you're taking the electricity from the outlet or whatever, and you're trying to recharge them and to put in the energy electrolytically. That's a non-spontaneous reaction. You need something to drive that process, and that's your outside energy source. Okay, so let's quickly talk about what these cells kind of consist of. So let's go ahead and look at this sort of contraption. Let's look at this battery contraption. All right. So this is your battery or your voltmeter to measure your voltage. Your electrons are flowing. Cool stuff. We have something known as a salt bridge. And then, yeah, okay, so now let's kind of look into this. So we have electrons flowing. It doesn't matter what type of cell you're talking about, electrons always flow from anode to cathode. The biggest difference we're going to see is if our anode is positive or negative, or if our cathode is positive or negative. But electrons always flow the same way. So we have our battery, we have our voltmeter, our voltage, whatever. Okay, so now this is iron. Let's use another color to kind of see. This is iron right here, and this is Fe2 plus solution. And then right here we have Cu2 plus in solution, and we have copper. And our two half reactions that are kind of taking place right here are Fe is going to Fe2 plus 2 electrons, and then Cu2 plus adding 2 electrons to make solid copper. All right, this obviously is an oxidation, so we're losing electrons here from solid iron, and then we have our reduction always taking place at the cathode. Now, this is another thing. It doesn't matter if you have electrolytic or a galvanic cell, oxidation always happens at the anode, and reduction always happens at the cathode. And the E naught for each of these is negative 0.44 volts. And the E naught for this one is positive 0.34 volts. Okay, so that's what's kind of going on, right? And then we have our salt bridge. Now, just to kind of clarify, because this is kind of a rough topic sometimes, a salt bridge keeps the reaction neutral. So basically, because we have Fe2 plus ions in this solution and copper ions in that solution, we can kind of have negative ions going ahead and neutralizing this solution right there. And because these positive coppers are being plated onto this electrode, and we're losing kind of positive ions in the solution, we can take positive ions and kind of replace them back into the solution. So salt bridge just helps to complete the reaction, helps keep everything neutral. So that's kind of what it does. All right, so let's go ahead and take a look at if it was a electrolytic cell. So, excuse me, if our reaction was electrolytic, let's just use the same substances that we're using here. We have our salt bridge, electrode number 1. We have our electrode number 2. Cool stuff. But in this case, this is our anode, and this is our cathode, the same sort of situation. In this case, electrons are still always flowing from the anode to the cathode, right? But what's happening at each of these? Well, at the anode, we have copper right here. Oh, we have copper right here, and then we have Cu2 plus in solution. And then for the cathode, we're having F iron being plated on with Fe2 plus kind of being used up in that solution. And once again, we have our salt bridge. And as you can see, electrons are still always moving from the anode to the cathode. And in this case, our anode is our place of oxidation. And but in this case, it's a little bit different because we're going to take copper and we're going to oxidize it into Cu2 plus 2 electrons. And then at the cathode, we're going to take our Fe2 plus, add some electrons, and make some solid iron. Cool. So that's kind of what's going on in each of these. Think of this as like kind of like a rechargeable battery. And I think that's the best example. Or anything that you can kind of recharge because you're actually like putting energy in. But the difference between these two, the biggest difference is, like I said, going to be the sign. So obviously this is spontaneous, this is non-spontaneous, but the anode over here is negative and the cathode is positive. In this case, the anode is positive and the cathode is negative. Think about it this way. If our electrons are flowing from our anode to our cathode, spontaneously they would want to flow toward a more positive thing, which is the cathode. If our electrons are still flowing from our anode to our cathode in electrolysis, it's non-spontaneous, so they probably would not want to flow to something more negative. That's how I kind of like to think about it. So another key thing to know is that if this reaction is spontaneous, if we're looking at our galvanic cell, then we can say that our E naught is actually going to be positive, because a positive E naught means a negative delta G, which means spontaneity. So our E naught is nothing but, we can kind of write this over here, E naught, E of the cell is equal to E happening at the reduction minus E happening at whatever the anode is, whatever's being oxidized. So I would recommend you start with your table of half reactions, look at your E red minus your E ox. So E of the reduction in this case is going to be this guy right here. So we're going to take E red minus E ox, which is equal to 0.34 minus negative 0.44. And you can see how these negatives cancel out, giving you a positive 0.78 volts. In this case, we're going to use the same formula, but in this case, we have something else going on with our reduction. So we're going to take E of the cell is going to be E red, but in this case, this one's being reduced, which has a voltage of positive 0.34. I'm sorry, this is being reduced, my bad. This is being reduced, which has a E naught of negative 0.44 volts. Subtract that by 0.3 volts, which is at the anode, which is the ox, is going to equal negative 0.78. And that negative tells you it is non-spontaneous. So that's your another kind of key factor that's going on. All right, last thing that you all should know, just quick little tidbits about galvanic cell. You're basically gonna load stuff on the left, and you're gonna drive that reaction to the right until your battery is dead. Until the battery is dead. All right, and we know it's spontaneous, which means negative delta G. We kind of covered that. All right, so this one, basically it's important because it converts chemical energy to electrical energy. And then it's basically taking like a battery, like the alkali energizer batteries that you get at the grocery. You're taking a battery to basically power a device. And then this basically produces electrical energy. Think of the battery you have that you're using up in your phone right now. Spontaneously, it's producing work, it's producing electrical energy, it's making your phone run. Now, usually it's also a super explosive reaction sometimes. So think about 2Na plus Cl2 kind of making Na 2Na plus 2Cl minus. This doesn't usually happen. It's super, super explosive. All right, so now this guy right here, this is obviously non-spontaneous, so we need an external power supply for this to happen. So think about recharging your phone after it's dead. You're going to take that external power supply and force electrolysis to happen. We covered that it's non-spontaneous, which means it has a positive delta G and a negative E naught. And in this case, we're taking electrical energy to chemical energy. And think about charging up a rechargeable battery. And from a wall outlet. Let's just go ahead and write that out. And last thing, kind of what we talked about, you need some sort of electrical energy for this to occur. All right, and so think of table salt, like making an explosion and deadly gas. It doesn't directly happen. So 2NaCl making 2Na plus Cl2, this does not readily happen. This is not happening, meaning it's non-spontaneous. All right, so that's kind of the general idea. Here's the final look at both of these, and these are kind of super fundamental, important topics that is good to kind of know. Remember, the big ideas that we have behind the differences between these two is the fact that one of them is spontaneous, one of them is not, and the fact that our signs are going to be different. However, electron flow is still the same. The way that we construct these batteries in terms of the salt bridge and the electrodes and what's happening, what's the cathode, is all going to be the same. But it's just what's reduced and what's oxidized depending on how much energy you have available. That does change. Well, hopefully that was helpful and hopefully y'all enjoyed it. Please subscribe, and I will make more videos, and let me know if you want any specific videos. All right. Thanks, guys.